everyone. Very welcome to this webinar this afternoon. My name is Manasvi Srivastav, and I'm the chairperson of Engineers Ireland Young Engineers Society. And this webinar has been organized by Young Engineers Society and is about wind farm construction. And I'm delighted to introduce our speaker here, Zoe Cooney, who has more than 8 years of experience in delivering renewable energy projects including wind farm and solar farm projects. She is working as a project manager at AFRI, where she manages small scale and large scale projects from financing to commercial operation. We'll have a Q&A session at the end, so I would encourage everyone to please write any questions, and we'll discuss them at the end of the presentation. And without further delay, I'll hand it over to Zoe.
Thanks, Manasvi. Good afternoon, everyone. Thanks for joining. As Manasvi said, we're going to take a quick run through wind farm construction overview. If anyone has any questions, put them in the Q&A and we'll try to get through as many as we can at the end of the presentation. So as Manasvi said, I've worked in renewables for over 8 years, and when I first started, the turbine size on my first project was about 1.85 megawatts. Since then, turbine production has increased and technology has improved. And in recent projects across the board, we are seeing up to 5.5 megawatts per turbine. So technology is moving a lot. The amount of turbines needed to produce the same amount of energy is reducing, and the turbines are getting bigger. The first time I was on a wind farm site, I took this photo from the bottom of a turbine. From seeing them in pictures or seeing them from far away in the distance, they don't look that big. But I remember the first time I stood at the bottom of one and looked up, I realised how big they really are. Here's another photo then from just far away. It doesn't look so big. Majority of these photos now might give a misrepresentation. A lot of them have blue skies and sunny skies, but unfortunately that's not how it usually works in Ireland. A lot of the sites, there's rain and clouds majority of the time. Just a quick introduction then to the summary of the life cycle of a wind farm. So this information on this slide has been taken from a Wind Energy Ireland report that was published in March 2019. So feel free to look that up afterwards for more detailed information. The quick summary then at each part of the wind farm life, how long each stage typically lasts and who is involved at each stage. I'm going to take a quick run through the pre-construction and construction in this presentation. But going through the full life cycle, we are looking at stages such as feasibility, planning and permitting, the pre-construction, construction, commissioning, operation and decommissioning. And as you can see there, we have some timeframes against each of these. So they range from 2 months up to the operational life then of approximately 20 to 25 years. But from feasibility to commissioning, you're looking at maybe anything between 48 for the planning, and then the additional few years for all your pre-construction, construction and commissioning. So developers, it is quite a long time frame from the concept of developing a wind farm to actually seeing the turbines on the ground and spinning. A summary on the pre-construction stage then. So the pre-construction stage is defined when the project has all the required permits and consent. So that will include your planning permission, all your land options with landowners, your grid connection offer with EirGrid or ESB, and a suitable commercial offer to sell the renewable electricity at the back end once you're into operational. So an example of that would be RES. And generally that proceeds into the pre-construction stage, all of those applications and permissions. Generally then they'll include the preliminary construction design, selecting your consultants and your contractors, obtaining all other permissions needed to construct and operate the project. So in addition to these, you could have felon licenses, which I'll cover a little bit more in another slide later on. You might need a section 50 for any water crossings and anything kind of along those lines. The planning permission compliance then also needs to be prepared. So whenever you get your planning permission, Similar to if anyone was ever doing an extension on their house or doing a building for yourself personally, and there's conditions for every plan and permission. So the developer needs to respond to all of those conditions to the council, and that's getting planning compliance with every condition. And finance is also considered at the pre-construction stage. So a developer could develop off balance sheet, which means they have the funds in their bank account, or they can develop it with project finance. So that's similar to us getting a mortgage to buy a house, and they lend the money from the bank and then they pay that back over a certain duration. So if project finance is used as an option, this will include legal and technical due diligence. Balance sheet will also include legal and technical due diligence, but it's different. The banks will have a full legal company and technical company, and we'll have to liaise with them throughout the course of the financing of the project to ensure that the banks are comfortable with all the contracts that are in place and that they're happy that the development can take place with the contracts that have been agreed. In the construction stage summary then, so it will generally follow pre-construction. However, for bigger projects, we do generally overlap pre-construction and construction. So particularly in the bigger sites, if there's, for instance, 20 turbines, we could have design ready for a quarter of the site. So maybe say for access to 5 turbines, foundations, hard stands, etc. Construction can then start on that section, and the design goes on in the background in parallel for the rest of the sections, and then construction follows on once the first part is finished. So generally the longer project the programme can be quite extensive, so we try and overlap pre-construction and construction. The construction stage then is generally the period of the highest employment and the most expensive. So as you can imagine, there'll be all of the contractors, all of the materials, all of the plant are used in construction, so it's the most cost intensive period of each project. It can also support a lot of local companies and create local employment. So we'll go through that in another slide, a few examples of how it supports locally. And in terms of the overarching programme, it could take around 1 year to construct a 30 megawatt wind farm. The bigger wind farms now, you could be looking between 60 and 100 megawatts, maybe even more. So it can take up to 2 years for the bigger projects then to be constructed. Sorry, froze there. Just another few wind farm photos then. So in my particular job, we also carry out turbine snagging, or that's kind of at the back end at commissioning before it goes into operation. So that's just a few photographs then from up the top of the turbine around the nacelle, and you can see here the rest of the wind farm and another couple of turbines here. So they're quite high up when you're up on the nacelle. That's another few, as I said, unfortunately misrepresenting Irish weather. Most of them are blue skies and sunny. This was one particular day. It was very, very cloudy, and the clouds were actually below the nacelle of the turbine. So it was quite a sight, and it was quite weird to be up on the top of the nacelle and not being able to see the ground. Local services then that I referenced previously. So most wind farms or most developments they try and support locally as much as possible. It also obviously it benefits the community, but it can have a cost impact on the project. If you're only transporting materials and concrete from a near quarry or near material plant, then it's obviously going to cost less for the transport. So digger drivers, truck drivers, builders, any sort of labour that can be sourced locally, that's the preference. Materials such as stone for the foundations, roads and crane hard stands, that's all tried to be sourced locally as well. Concrete for any of the foundations, the substation foundation and any bridges that are constructed, any other supplies, any hire of machinery and plant. Generally there'll be a site compound for each contractor, so they have to rent out the site cabin and facilities, waste disposal, skips, diesel for all the machinery, cleaners always come to the compound, any food for the people working on site, so either food can be brought into site or any of the workers then, if they're popping out for lunch, that will all support the local economy. Accommodation for workers. Lots of people then, wind farms can be in quite rural areas, and rather than traveling back and forth every day for long days, a lot of the construction companies then will have workers then renting close by to the site. And site security then, so most contractors will have site security outside of the normal work hours, so that will include both CCTV towers and also personnel who can be stationed at the site 24 hours a day or just outside of the work hours, just to make sure that everything is safe during the construction period. Project program. So whenever the program is being drafted at the very start, there's a number of considerations. So generally it will start with the civil works. So all of the roads, the substation and the turbine foundation and hard stands have to be constructed civilly before the turbines can actually come to site. The grid connection works then can start around the same time as the civil works. So the substation can be built and all the trenching and duction for the grid route then, before the electrical cables are installed, can be commenced. The substation then building, once it's ready, that's electrically fitted out. So there's a lot of electrical equipment that needs to be installed. And when the road and foundations are ready, then the turbine supply and installation contractor will start deliveries and turbine assembly. So you can be looking at between 9 to 12 months from when you sign a contract with the turbine company to the turbines actually arriving on site, and that gives time for all the civil construction in the background. Other considerations then is if any special licenses need to be applied for. So as I mentioned earlier, felon licenses might be required for the construction. So it could be an area where there is a part of a forest near the site, could be along your delivery route also, or it could just be a road open license for all of your trenching for your grid connection. Section 50 then for any water crossing, so they all have to be applied for and granted before those particular works can be carried out on the ground, so that needs to be considered. Any site investigation, so for a lot of the design, site investigation is needed. The designers need to know exactly what ground they're working with, so that will form the basis of this, particularly the turbine foundation design and any of the roads. So that SI works will need to be considered in the programme to be all completed before the design can commence. If there's any landowner agreements that are needed, so particularly for you generally have your land agreements in place for planning of the actual site that you're developing on, but there can be additional agreements needed for any of the people along the delivery route for the turbines. So the turbine components can be quite large, and the blades, for instance, in the bigger turbines now can be 74 meters long. Obviously, the delivery of a 74-meter blade around some of the country roads can be quite tricky. So some land agreements have to be made, cutting back hedges, all that kind of thing. So all of those agreements need to be in place. And then the strategy for the turbine install needs to be considered in your programme. So the time of year that your turbines are going to be installed is quite significant. Generally in the summer, obviously it's better weather, the days are longer and brighter. The winter then, naturally the weather is a little bit more windy, there can be storms, can be high gusts. So whenever you're doing your programme and when your turbines are expected to come to site, the amount of wind delay days incorporated into the programme is very dependent on the time of the year. The amount of cranes then that are agreed with the turbine company also need to be considered in the programme, and the blade lifts, how the blades are going to be lifted needs to be considered to properly plan out your programme. So there's generally two options or two high level options that you can do for your blade lifting. You can put your hub up onto the nacelle first, so you have all your tower sections installed, your nacelle, which is the big box at the top, and then you have your hub, which is what we call the nose, and that sticks out of the nacelle. Hub can be installed in one lift. Then each of the three blades are all installed in separate lifts. The other option is if you have your hub or your nose on the ground, you install all three blades into that and bolt them on and torque them and everything. and then that's lifted in one go. So that can also be referenced as a star lift. That will obviously impact your program if you're doing one lift instead of 4, but consideration has to be given to what kind of site you're on and what the weather is going to be like. Lifting individually, you can lift at higher wind speeds than you can lift for all of the blades on the hub in one lift. You have to have quite low wind speeds for that, so it's not as common here in Ireland. And then just rough timeframes then for your program and how it all looks at the end of the day. So the contractor could build between 100 meters and 200 meters of new wind farm roads each day. And there can also be existing roads on the development. So it could be, you know, a forestry track or just a general small driving track, which will be a little bit quicker. The construction of the substation building. So mostly we would see 38 kV or 110 kV buildings. So the 20 or 38 kV buildings would take around 12 to 16 weeks to civilly build, and then it can be up to 20 weeks for the 110 kV buildings. So generally on 110 kV projects, you'll have 2 buildings, and one will be the EirGrid or ESB side, and the other will be the developer side, and they're usually separated by a fence. The 38 kV then, it's one building. Part of the building is for ESB and the other part is for the developer, and that's all fenced off as well, kind of the middle of the building, and it's locked up. So ESB area in both 38 and 110 can only be accessed by ESB once it's handed over into operation. For the construction of the turbine foundation, so it takes roughly 1 week to excavate out for the foundation area. It's about 1 week then to tie all the reinforcing steel, and then the concrete is poured and it needs 28 days to cure. So quality inspection of all the cube test results from a lab have to be inspected before the turbines are installed on the turbine foundation, just to make sure that the 28 cube result is as per the strength that the foundation has been designed to. Also, some of the roads might need to be dug out from elsewhere within the site, so that needs to be considered in the programme. If there is a borrow pit or a quarry within the site that's planning permitted, the developer can take stone from that or any other materials that they need for the construction. So that will be considered in the programme. It takes quite an amount of time, obviously, to break out rock and stone from within the site. So that needs to be planned in advance of when the roads are actually going to be constructed and that material is needed. Also considerations around building or replacement of bridges. So there could be some small streams or rivers either within the site or along the turbine delivery road. All of that needs to be checked to see if it's sufficient in terms of the axle strength. So anything that's going over that, the bridges need to be able to support the weight. So some bridges might need to be completely replaced, or some of the streams, especially within the site, may not have an existing crossing, and a bridge needs to be fully constructed and designed. And some of the public roads, particularly for the turbine deliveries, might need to be widened. So all of that needs to be considered in your programme to make sure that back end date when you need all your turbines installed and you need your electricity export, you kind of need to work back and consider all of these. In terms of the actual construction of the turbine components, so up here that's kind of up to the foundation, and when all the turbine components are actually on the site and set on the side, the crane is brought to site and the crane starts to construct it. So it would generally take around a week, assuming that all the towers are lifted up, usually 3 to 4 towers per turbine, depending on the turbine size and the supplier. Then we'll have the nacelle up on top, then we'll have the hub, and then we'll have the blades installed. And that roughly takes a week if we're in decent weather. If there's extensive wind delays, if the wind is too high to lift components, that obviously impacts that, and it'll take longer. So project design then, so designs are prepared for the following key aspects of the project, and as I said before, the design timeframes all need to be considered before the construction starts, and the design and the construction can be going on in parallel once the design has started in a certain section to allow construction to commence. So the road and the hard stand, so there'll be a geometric design needed for all road and hard stands. So that means if you're changing the gradient of the existing road, the gradient needs to be considered for turbine delivery. There's a limit to the gradient on the road for turbine deliveries. There can be an additional few can increase by a little bit if you have towing, but there's still a limit to the gradient of the road whenever you're using towing for the component delivery as well. The turbine foundation, the design of the foundation can need verification by another foundation designer. So that's generally a key point if the developer is getting bank finance for the project. The bank will want the foundation designed by the developer's designer to be sense checked by another competent designer, so generally another company. Bridges for any streams or rivers on the site or along the delivery route, then all of those designs need to be considered, and also, as I previously mentioned, then the section 50 will feed into that design timeframe as well. Site investigations can also be required to finalize the design. So for example, some site investigation might have been carried out, but more detailed site investigation might be needed to completely finish off the design. And the biggest concern around site investigation is when there's peat on the site. So when there's peat on the site, checks can be carried out, which include ground penetrating radar. So that tracks the peat depth. And as you can see here, it's color coded along this road. That's given different delineations of the peat depth. So the design needs to incorporate that peat depth into it. And that's how the results of the report from the radar looks like in cross section then. For bridge design, so this is what a sample bridge design will look like. So you'll have your cross design on the top. So it'll show the width of the bridge. It'll show then how far away it is from the water. And then down at the bottom, it's just our plan, kind of showing them how the bridge interacts with the planned site road. Geometric design then, and this is a sample of what the geometric design will look like. So the cut and fill then to change the gradient of the road is delineated in green and red. And you can see down at the bottom here on the cross section of the road, that kind of greeny coloured line there is the existing road gradient, and then the red line and the green line in the background is showing the new gradient of the design. So this is generally then every section of the wind farm development will have a geometric design for the road and the hard stand. For the foundation design, so it'll look something like this. You can see the cross section of the turbine foundation in the middle. It's a pedestal. From what you can see at the top, it's quite small. Underneath the ground then there's quite a large concrete pedestal, and that's all backfilled with stone. So on the ground level, all you can really see is that little middle bit at the center. At the top then, it's just given general dimensions, and the bottom then is specific details within the turbine foundation design. There's a separate design sheet then for the steel reinforcement, so that will show all the rebar around the top, so that's in both directions to give an indication of the spacings. And then down the bottom, it's a cross section of the steel then from the middle of the foundation out to one side. So that cut down the middle, it'll be the same left and right. And the little dotted line along the bottom, that under the foundation, that delineates out the ducting. So ducting needs to be incorporated into the turbine foundation design and construction to make sure that there's ducting in place when the concrete cures in the foundation to allow the cables to be pulled in from outside the turbine foundation up into the basement of it. Contracts then that are considered in wind farm development are generally based on FIDIC yellow. So the standard conditions in FIDIC yellow are followed. There can be an additional document for each contract that's particular conditions. So if FIDIC says something in clause 2.1.1 and we want to slightly amend that, we'll have a particular condition document, and that will reference clause 2.1.1 and say delete last line of this and replace with XYZ. or you can delete the whole clause and propose a whole new clause. So there'll generally be the general conditions of FIDIC along with the particular conditions for each contract. And in terms of the contracts that form wind farm development, so generally then there'll be a project manager. So that could be someone like ourselves in AFRE that's contracted out to, or the developer might have their own in-house project manager. So a lot of the bigger developers will have their own project management team. There can be one contractor then who does everything on the project, which is an engineer, procure, construct, so an EPC contract. However, the most common is either 3 or 4 of these bullet pointed contracts here. So you'll have a separate contract for wind turbine supply and install. There'll be a civil contractor, so that'll be design and build. And then these two are either separated out or they can be combined together. So there's an electrical works design and build contractor, which will be for the substation. And there can also be a separate contractor then for the grid connection. So that'll be design and build for the grid connection between the substation that's being built on the site and to where then it's connecting into an existing ESB or air grid station or substation, or it also can be connecting into an existing overhead line. So these bottom two can be separated or they can be combined together depending on the preference of the developer. And for these contracts to be put in place, there can generally be a tender process. So each developer is different. Any of the semi-states will have to go through public procurement. So there are set timeframes in terms of what documents need to be issued out, how long a contractor has to review all them and provide a quote back. Some independent developers then will have their own timeframes, and other developers will have contractors that they're used to working with and they want to use them on the next project. So it's not an extensive tendering period by any means. So the type of developer all depends on the time frame of the tendering to get those contracts granted in terms of confirmation of who the contractor is going to be. And then there'll be a time frame to get all the contract documents agreed then with each contractor. Outside of those key 3 or 4 contracts, then there are a number of other people involved. So there will be a bank's engineer to monitor the project. So that's generally if there's project financing, i.e. the mortgage, the borrow of the money for the development. There'll be an archaeologist, geotechnical engineer, all the environmental, so ecologist, ornithologist, hydrologist, and noise monitoring. There can be a community liaison officer to keep the local community informed. It's quite important for the developers to keep the local community informed, particularly in relation to any considerations from planning. There can be opposition across the country. Thankfully, we're seeing that less and less, and most people are getting used to the wind farm development and also realising the benefit of them, particularly in relation to meeting our 2030 targets and beyond. But also just generally, it's better for us to rely on the renewable energy in Ireland, and particularly that we're such a small country. We have such a big border for wind, it's worth capturing all that. And there can be safety consultants then to make sure that the project is built safely. So every contractor will have to have a health and safety team. There can and generally is also an overarching safety company then coming in to inspect them to do audits quite regularly and to carry out reports then and just make sure that all the contractors are complying with all the safety requirements. This is a photograph of what I mentioned before, so either a borrow pit or a quarry. So these will be defined in the planning application and planning permission if these can be used. It's quite useful if a project does have this because it means that you don't have to go out and constantly be getting material delivered to site. It can be taken out from the site itself. As you can see here, there's quite a lot of machines needed to extract all the stone to build the roads, foundations and hard stands. And then obviously trucks then will be needing to be, the dumper truck here needs to be driving then through the site, and that's actually quite constant whenever the rock breaking is going on. So there can be a lot of activity here to get all the material needed to develop the site. There might still also be additional stone required to be imported from nearby quarries. Obviously, all the stone has to be tested and a particular spec according to the design to be used on site. So that all needs to be lab tested as well. And that's a photo of the turbine foundation. So this is the rebar is all in place, and the foundation pour then is just starting in this photo. And that's just the pour then from another angle. Once the concrete is cured then, and the turbine foundation has been poured, this is generally what it looks like. So from the design, this section here is the pedestal that I was mentioning. So all of this is backfilled up to ground level, and you'll only see this little bit here in the middle. Quality checks during construction. So of course, safety is the biggest priority on site. So health and safety is very important to make sure that quality checks also are carried out. There can be inspections on quality throughout the construction. So generally, those kind of checks will include survey of the roads for the gradients, just to make sure then the construction is per the design. That's particularly important with bigger components, and if there's any towing needed. And as I said, there's still a limit to the gradient of the road, even if towing is going to be used. Any roads, hard stands that are constructed need plate bearing tests. So it needs to be proven that all of the roads and the hard stands have the correct bearing capacity then for all of the deliveries along that. The duct proven then, so once the ducts are put in trenches, so for both the collector circuit, which is all of the cables going around the turbines and connecting them all back to the substation, and also for the main grid route, which is between the substation on the wind farm back to the ESB or grid building. All of that plastic ducting needs proved before the cables are put into it. So generally the proving will have a winch, and it'll have a sponge and a brush. So all of the ducts are cleared out of any water or any depositions to make sure then whenever the cable is pulled through, there's no stones or anything in it that might damage it. And then quality checks on the delivery route. So there will be a delivery route survey at the very start to identify what delivery route is planned. Then any of the land agreements and any of the works that need carried out, any widening of roads, any hedge removals, any wall removals, all of that needs to be carried out. And then there's a final delivery route survey to ensure that all of the turbine components can be delivered to site safely, and particularly the blades, because they're the longest component. This is a photograph then of the substation building on the site. So as you can see here then, there's a number of different doors. So there's a number of different rooms within the substation. The compound then generally is just stoned off. There is generally a fence then, a palisade fence put around the building, which is locked. This is a photograph of the cable on the spool. So this will be part of the grid connection, the main grid connection. So generally in the ground, in the duction then, whenever you're designing your main grid connection, there will be joint bays every 800 meters to 1 kilometer. It'll depend exactly on the distance of the joint bays depending on the design. But for example, if you have a 10-kilometer run of cable, you'll be expecting around 11 to 12 joint bays. So whenever the cable is actually being installed, it's installed between 2 joint bays. So there's a winch set up at each end. The cable is pulled then between the 2 joint bays, and then it goes on and then installs the next set of cable between the next 2 joint bays, and that continues on then until cable is installed from the wind farm substation the whole way across to the ESB or grid station, or up to an overhead line. And the main reason for this is to ensure electrical safety, of course, but also if you ever have any issue on your cable, if the cable is put in sections between joint bays, if one part of a cable, for instance, a stone damaged it and it needed to be replaced, it's much better to replace a section of cable between 800 meters to 1 kilometer than it would be for a full cable route that could be up to 20-30 kilometers. So that's the reason the cable is pulled and has joint bays along the route. This is a photograph then of one turbine foundation turbine location. So you can't see it very well in this photo, but this is the foundation, this little circle bit up here. You then have your hard stand just off the foundation. So the orientation of the hard stand is always that it's just right off the foundation and these hard stands are generally between 40 and 50 meters wide, sometimes wider, and about 80 to 100 meters long. So they need to be so big because all of the components are to be set down on the hard stand. The crane then needs to be set up around the middle of the hard stand, and then the crane is kept in the one place and it swings around and lifts all the components up until the turbine is fully installed. And generally the plate bearing test that we do, we try to design in where the crane pads are going to be, so where the crane's going to be set up, and a plate bearing test then is carried out at each corner of that, and then another few plate bearing tests around the rest of the hard stand are carried out to make sure that everything is as it should be. And the blades here then, so outside of the hard stand where we have all the main components, we have what we call blade fingers. So they're little kind of long fingers, if you like, just built off the hard stand. So that's where the blades are set up. So there's little systems set up so that the blades can be hooked on each end of the blade finger. Generally the ground in between these two blade fingers is about 1 meter below the blade finger height, and that means that someone can get in and do an inspection of the blades before they're installed up on top of the turbine. Sometimes there can be, paint missing, scratches, anything like that from delivery of the turbines and the offload from the delivery truck. So it's better to have all of that inspected before the blades are up in the air, because a special rope access team will be needed then to do any remedial works if that's needed. So this is a photograph of the crane set up on the hard stand. So as you can see here, then all the tower sections have been installed. The crane pads, you can see those set out on the ground as well. And then after the towers are installed, the next installation will be for the nacelle, then the hub, and then the blades. And that's the hub down on the ground, with one of the blades installed into it. The other two blades then are sitting nearby and they're going to be connected in as well. And this was where a star lift was going to be carried out. So one lift for the hub and all three blades up in one go. Coming to budget then. So the cost will vary for each project, but roughly speaking, a 30 megawatt wind farm could have a construction budget of approximately 39 million. So roughly speaking, 1.3 million per megawatt. Now that's just the construction cost. That's not any other costs around planning or any SI that's needed or anything else the developer needs to do. This is purely just construction, so it's quite expensive. And how that's broken out then, it's around 70% for the turbine manufacturer, supply and installation. So for that contract is about 70% of the construction cost. Civil works then 8 to 12, electrical 10, project management, insurance, council fees, and that's about 3 to 5%. And then there's always a contingency set aside, which is generally around 5%. There's always going to be unknowns that come up through the course of construction, so contingency has to be sitting in the background for that. Yeah, that's just note that the development cost and pre-construction cost are all separate to that rough estimate. Of course, every project is different. That's only a rough rule of thumb. So, that price can vary per megawatt. Once construction is completed then, so you have your substation built, your grid connection, your cable pulled through that, you have all your turbines up and running, project commissioning then comes then at the end. It's carried out under the same main contracts. So if you have 3 or 4 main contracts, then there'll be 3 or 4 different types of commissioning. So each contractor will have their own specialised commissioning team. And commissioning can take anything between 2 to 6 months, depending on the size of the project. So when the project gets connected to the grid, so we call that energised. So that's when it's switched on at the wind farm side and on the other side of the EirGrid or ESB. And everything is live and there's power. We define that as being energised. Once the project is energised, then it begins obviously putting renewable electricity onto the grid. But there has to be a number of grid code tests carried out to make sure that the wind farm is performing to the specification that ESB need. And that's to make sure that there's a secure and stable electricity grid. and it's particularly important in Ireland whenever we have an island grid. So generally, once we energise, we're limited to probably around 5 megawatts by EirGrid and ESB. Each stage then needs to be tested. So for example, if it's a 40 megawatt project, once we're first energised, we'll be allowed to export 5 megawatts, and then generally tests are carried out every 10 megawatts in additional to the 5. So the 5 megawatt test will be carried out. If that's all okay and everything is approved, the wind farm can then export 15 megawatts, and that's then checked and tested. And if that's all approved, it'll go up to 25. So it'll keep jumping up in increments of 10 until it reaches the full MEC, which is in the grid connection agreement. So all of these tests are carried out on the grid. For the turbine then, so the turbine undergoes a series of performance and reliability tests to make sure that the turbines are performing as they should be. So we test to see if the turbine output matches predictions. So there will generally be a power curve in the contract whenever the turbines are first purchased. So that will generally be an expected output per meter per second of wind. So you'll kind of see a curve in the contract, and we'll check if the actual export is aligned with this. The turbine then will need to be tested for either 120 or 240 hours without any significant fault or breakdown. So the 100 hours or the 240 hours are defined in the contract at the very start when we're agreeing that. Generally, 120 hours is for any turbines that there are a large number of them already in Ireland, so the same type. And the 240 hours then is for any newer type turbine that's coming to Ireland. So the timeframes will differ on the testing because of that. And the photos then that I had shown from the walkdowns or turbine snagging, as it's sometimes called, that's also needed to be carried out by the project manager or the project engineer. And what that involves is it's a visual inspection of each turbine. So we'll go into the turbine and before it's energised, we can access the basement. So we'll go down and have a look and make sure that everything is as it should be. All through the turbine, then we'll stop at every floor. So there can be 3 to 5 floors throughout the tower section. Then we go up into the nacelle, make sure everything is in the nacelle. So generally we'll be checking for all of the safety signage, fire extinguishers, first aid kits, make sure there's no oil spills, any of the oils that are needed to check all the levels to make sure everything is topped up. And we'll go into the hub, which is the nose. So the bigger turbines, you can access the hub through the nacelle, which is great because you don't have to go out over the top. But some of the smaller ones, you have to climb out to the top of the nacelle. You have to open the little hatch and get into the hub. So we'll have a check of that. All of the bolts that are connecting all of the tower sections and the blades then, they're visually checked to make sure that they have been torqued. And there's generally a spray paint or paint strip on that by the bolt torquers, confirming that they've did all their checks. And there'll also be lots of lifting eyes within the turbine itself and out on top of the nacelle. So generally those are little yellow hooks, and that means that we can use them to hook onto with our harness, and they'll generally have a tag to say that they have all been tested, so they're safe for us to hook onto then whenever we're going out on top of the nacelle and within the turbine itself. So that's everything from me. Thanks everyone for your time.